Hello, Ross. For lesson 3.1, instead of doing a specific example, I think I want to talk about the theory and the need for this algorithm because it's our textbook treats it differently than curve sketching algorithm. But we like to introduce it in curve sketching because we feel like the topics are related. But really, we're going to need this algorithm when we start optimization problems. So I don't want to do a full optimization problem. I just want to revisit what's hopefully a familiar advanced function situation with you, and then we'll illustrate why we would want to use the extreme over an the extreme over an interval algorithm. So I hope you've seen the construction of open top boxes before. We'll go through a full example like this in class when we start optimization. If you have a rectangular sheet of material and you cut congruent squares from the corners, you're then left with a net that you can fold up to create an open top box. Its volume is then given by this cubic. It was one of the first applications of cubics that we saw. Now imagine the questions: find the maximum and the minimum volume. If we're just looking at a cubic function, this should cause us a little bit of pause because cubic functions don't have absolute maximae or minimae because of their opposite end behavior and their odd exponents. But in terms of this application, I hope it's relatively clear what the minimum volume of a box is going to be. And then we'll visualize how we find the maximum volume. So being able to draw this curve, this is a polynomial curve. We don't really need too much calculus to get a really good idea of what this curve is going to look like. We would depend on its roots or its h-intercepts. We've got a root of 0, a root of 40, and a root of 50. 0, 40, and 50. We just be careful here. These are leading negatives, but with those two leading negatives multiplied together, we will have a leading positive coefficient. I can't just look here to figure out my leading coefficient is positive. Which means that as h decreases, I would expect my volume to decrease, then my volume will increase. I've got 3 linear roots. I feel like I need to turn a little bit earlier here so that I can inflect and come down through there, showing me that I don't think my maximum is going to be happening at 20, but maybe a little bit more to the left from there. And then looking at this application, I hope, again, in advanced functions, we have the opportunity to discuss the domain of this application. Because this function tells me that if I cut negative distances from the corner, that my volume will be negative, and that doesn't really interest me too much. It also says if I want to make my volume larger, just keep cutting. If we look at this carefully, if we think about the fact that we don't want negative volumes, maybe we can see why we wouldn't want cuts greater than 40, because then one of our dimensions would be negative, and it's not possible for our dimensions to be negative. So the volume curve for the application actually only looks like this. It has an endpoint there. It'll climb to some absolute maximum now. Used to just be a local maximum and then fall down to the same absolute minimum that we saw right here of 0. So there's the application of the V curve. Our interval then in this question is going to be, h values. We could talk about whether it should be greater than or equal to or greater than. We don't really care too much. Isn't going to affect any of our conclusions. Cut depths need to be between 0 and 40 centimeters. So that's why it's important that we're talking about over an interval here, because this curve on its own isn't going to have an absolute maximum, but over a fixed interval, any continuous curve is going to have an absolute maximum. Also, there is going to be a minimum volume. Asking you to find the minimum volume in this application should be a relatively easy question. I hope you can see the minimum volume that you can make is going to be 0. But the algorithm will tell you that. You would evaluate v of 0 and you'd get 0. You'd evaluate v of 40 and you get 0. You would set v prime of t equal to 0, and that would tell you this point, let's call it a, comma v of a. You would evaluate v of a and figure out that your maximum is going to be v of a. And that's how the algorithm is going to work for us in word problems. Now, usually because of our knowledge of an application problem, we might not need to actually run the algorithm in its entirety. to identify what the largest and what the smallest outputs are. In some cases, we're only looking for the largest as well, but it'll always be there. So give it some time. Let's say just review the wording of the algorithm.